Hi, this tutorial is the fifth in the Pharmacokinetics series. In this video, we'll be discussing excretion of drugs. Excretion is defined as the irreversible removal of drugs from the body. There are two main ways in which the body excretes drugs. One is via the hepatobiliary system. This is when the liver excretes a drug or a drug metabolite into the bile, which in turn gets excreted with the feces. An example of a drug which is primarily excreted by the hepatobiliary system is the antibiotic rifampicin. However, most drugs are primarily excreted by the kidneys. As such, we will focus on this system in this tutorial. In this system of excretion, a drug gets filtered into the nephron of the kidney. If you want more information on the details of this, check out the nephron function tutorial and other kidney tutorials at handwrittentutorials.com. Once the drug is in the nephron, it flows through the nephron into the collecting ducts and ultimately out of the body in the urine. So we can define some values here. First of all, there is a certain concentration of the drug in the plasma. We'll denote this Cp. Secondly, there will be a certain concentration of drug in the urine. We'll denote this Cu. Finally, there will be a certain rate at which urine is being produced. We'll denote this rate Vu. From these values, we can determine the clearance of a drug. The clearance of a drug is given by this formula. Clearance equals the concentration of a drug in the urine times the rate at which the urine is being produced divided by the concentration of drug in the plasma. The clearance is often very difficult to understand conceptually, so I'll try to simplify it as best I can. This equation asks, how much plasma contains the amount of drug being cleared at this time? The concentration of the urine times the rate at which urine is being produced shows how much of the drug is being cleared from the body at any given time. This is the top part of the equation. When the bottom part of the equation is factored in, it will give us a volume of plasma per unit time. Thus we can say something like 500 ml of plasma is being cleared of the drug per minute. Another way to think of clearance is, if there is a certain amount of drug in the plasma, how quickly can I get rid of it? The clearance answers this question for us. So let's look at the factors which affect these values. The concentration in the plasma is primarily related to the dose of the drug being given. The more drug, the higher the concentration in the plasma. The volume of urine produced is mostly related to the glomerular filtration rate. Hence, people with kidney disease who have a low glomerular filtration rate will also have a lower clearance. Thus, drug dosing may need to be adjusted as they will not get rid of the drug as quickly as someone with normal kidneys. Now let's look at the concentration in the urine. Different things can happen to drugs as they pass through the nephron. If they are reabsorbed, then the concentration in the urine will decrease and the clearance of that drug will be reduced. Conversely, if the drug is secreted into the nephron, this will increase the concentration in the urine and also the clearance of that drug. An example of a drug that is actively secreted into the nephron is penicillin. Now let's talk about something slightly different, orders of kinetics. In the system I've drawn above, the higher the concentration in the plasma, the faster the drug will be excreted. This makes sense because the more drug in the plasma, the more in the filtrate, and thus the more drug in the urine. This will give us a curve that looks like this. So the speed at which the drug is being eliminated slows down as the plasma concentration drops. Note, however, that the half-life is a constant. When a drug behaves like this, we call this first-order kinetics. Now let's change the situation a little. As we saw in the previous tutorial, drugs often have to be metabolized by an enzyme prior to excretion. The system would then look like this. A drug gets metabolized by an enzyme, and then the metabolite gets excreted. Normally, the drug still conforms to first-order kinetics. However, in some situations, there is a limited amount of enzyme and too much of the drug. The enzyme saturates, meaning that it is all used up and is working at 100% of capacity. This means that if more drug is added to the body, it won't change the rate of excretion because there is no extra enzyme to process the extra drug. This effectively creates a bottleneck in the process, and the rate of excretion is now independent of the concentration of drug in the plasma. Hence we end up with a linear graph like this. Note that in this case, the half-life is not a constant value anymore. It is dependent on the current concentration of the drug. When a drug behaves like this, we call it zero-order kinetics. Drugs with zero-order kinetics are more easily overdosed because the rate of excretion doesn't increase with increasing dose. Ethanol is an example of a drug with zero-order kinetics, which is why no matter how much someone drinks, they will only metabolize about 10 grams of alcohol per hour. It is important to note that once the enzyme is no longer saturated, the elimination pattern will follow first-order kinetics, which is what is happening at this point on the graph. And that completes this tutorial